conditional probability and independence. To introduce the concept of independence, of conditional probability and then independence, let's begin with one example. Suppose that we have one experiment that is rolling a die. We know for this the sample space is given by 1, 2, 3, 4, 5, and 6. Now consider the event even numbers. Since we're talking here about this sample space, remember that an event is a subset of the sample space. So in this case, I have to consider the numbers even in the sample space. They are 2, 4, and 6. And consider the event B. Numbers greater than 3. In this case, we know that numbers greater than 3 in the sample space, they are 4, 5, and 6. And we know how to compute the probability for this, right? For example, the probability for A is only 3 over 6, or 1/2, or 50%. The probability of B is again 3 over 6, or 1/2, or 50%. But what about if we want to consider the probability for any of these two events, but not relative to the whole sample space? For example, remember that we can interpret the probability as a proportion of occurrence. I can say that the proportion of occurrence of even numbers when you roll a die is 50%, because we have 3 numbers out of 1, 2, 3, 4, 5, 6. That's why we have 50%. And the same happens for the event B. What is the proportions of occurrence for numbers greater than 3? Is 50%. That means that I can count 3 numbers greater than 3 out of the 6 numbers that I have in the whole sample space. But what about if now we modify this a little? For example, what about if I want to compute the proportion of occurrence of numbers greater than 3, but not relative to the whole sample space? Let's say that I want to do it only focus on the event A. It's like if I modify the sample space. Let's say that by now my sample space is going to be only this one, 2, 4, 6, and I want to compute the probability for B, or what is the proportion of occurrence for numbers greater than 3. Numbers greater than 3 here in this set, we have only 2, 4, and 6. So according to this logic, the proportion of occurrence would be 2 out of 3. That is different than the original, right? Relative to the whole sample space. So we have one probability for B, the one that we have known. Probability of B is 50%, but relative to the whole sample space. But if I consider only the sample space as A, or I restrict the sample space to one event, in this case A, the probability for B would be 2 out of 3. So we need to formalize these ideas. We want to compute the probability of B, but restricted or given A. In that case, we write it like this. What is the meaning for this? This is conditional probability of B given A, or probability of B restricted to A. And according to my previous reasoning, probability of B given A is how many numbers greater than 3 we have in this set. We have 2, 4, and 6 out of 3. So intuitively, my answer would be 2 out of 3. You see that? But of course, we need to formalize this, make it formal. So definition. The conditional probability of B given A is probability of B given A and is equal to the probability of the intersection of A and B divided by the probability of A. Notice in this definition how for the probability of B given A, we have to compute the probability of intersection and the probability for the second event A, the event for which we are restricting or redefining our sample space. Probability of A. But what about if I wanted to compute probability of A given B? In that case, in the top, always we're going to have the probability of intersection, but in the bottom you have to put the probability for this event, whatever the event is here. In our example, probability of A given B is the probability of the intersection divided by the probability of A. A intersection B is the elements A and B share, 4, 6, 4, 4, 6, 6. So, I also need the probability of A. The probability of A, remember, it is 50% or 1/2. So, probability of B given A is probability of A intersection B, that in this case is 2. Is 2 out of 6. So here is going to be 2 out of 6 divided by the probability of A. The probability of A is 3 out of 6. And if you compute this, you will realize that we can cancel this number, 6, 6, and what is left is only 2 out of 3. Notice or note that for this case, probability of B is different from the probability of B given A. Because probability of B is 1/2 or 50%, and probability of B given A is 2 divided by 3, or approximately 0.67%. Yeah, most of the times, many times we will know that you will realize that these probabilities are going to be different. Probability of B is going to be in general different from probability of B given A. Sometimes they're going to be the same, but well, we will talk about it later. But this is conditional probability. Now let's see some examples. Example, in a recent election there were 1,000 voters. They were asked to vote on 2 issues, A and B. The results were as follows: 200 people voted for A, 400 voted for B, and 25 voted for A and B. If one person is chosen at random from the 1,000 voters, find the following probabilities. So here we have some events. The first one is the probability voted for A given that he voted for B. So probability of A is going to be probability of A, 200 voted for A out of 1,000. It's going to be 200 divided by 1,000. Probability of B is 400 out of 1,000. The probability for the intersection, we're going to need it, is, notice, we have for the intersection, how many people voted for both, A and B, 25. So we have 25 out of 1,000. Then, let me do it here. For this one, probability of A given B is equal to the probability of intersection divided by the probability of B. Yeah, I'm following the definition. Notice how to identify that we're talking about the conditional probability. Most of the times you will see words like this one, given. Given. Given, if, restricted to. Those are words that suggest we have to use conditional probability. In this case, voted for A given that he voted for B. So we're looking for the probability of A given B. And you have to use this formula. Be careful. This formula is in terms of B and then A first. But here we have to compute A and B. A given B. So always in the top is going to be the probability of intersection, and in the bottom put the probability for the second event. In this case, since we have probability of A given B, I have to divide by the probability of the second event, that in this case is B. And then this probability is 25 out of 1,000 divided by 400 out of 1,000. And if you simplify this, you will realize that the answer is 25 out of 400, or this one, you see? Now, what is the probability of B given A? Probability of B given A is the probability of the intersection divided by the probability of A. In this case, it's going to be 25 out of 1,000 divided by probability of A, that is 200 out of 1,000. And if you compute this, this is going to be 25 out of 200, which is this one, you see? All right. Next example. It says 100 people were surveyed on one question pertaining to their educational background. The result of this question and their genders are given in the following tables. Many times you are going to see a table like this. They are called like a probability tables or contingency tables. But first, you have to be sure that you know how to read this. I think it's not very complicated. For example, it says this is about education and gender. So, for example, a person with a college degree, female, you locate the row college degree and the column female, and you will see that that number that with both college degree and female is 31. No college degree, and for example, male, you go to the row no college degree and the column male, and you will see that we have 15, right? And so on. This is how you must read this. Each cell that has to do with two concepts is going to be the number of elements in the intersection. How many elements are there in the intersection, for example, of college degree with male? 19. Right? So this is going to be important to compute the conditional probabilities based on these tables. It says if a person is selected at random from those surveyed, find the probability if each of the following of each of the following events. The person is female or has a college degree. All right. And the first one, we're looking for female or college degree. So we look for probability of female union college degree. How do I know this? Remember that when you see the word "ort," it's very likely it makes reference to the union, to the operation union. So that's why I put here F union D. And this probability is computed with probability of F plus probability of D minus the probability of the intersection. And now we can compute probability. For example, for female, what is the probability of proportion for female? We have to count we have to watch the total number of female. In this case, go to the column female and go down to the row total. You see that? It's 66 out of, what is the total in the sample space? 100. You see that? 100. So it's 66 out of 100 plus college degree, 50 out of 100 minus the probability of intersection. Intersection in this case for these two events is female college degree is 31. 31 out of 100. And the answer should be 66 plus 50 minus 31 divided by 100. And you will realize that the answer is 85 out of 100. That is the same answer we have here, right? Well, in this case, it is expressed like 1 minus 15 over 100, but it is 85 over 100. Now the next one. The person is male or does not have a college degree. So male or doesn't have a college degree. So in this case, we are computing the probability for male, union, no college degree. That in this case is denoted with the symbol D prime. You see? And we use the same formula. It's probability of male. How many male? 34 plus how many with no college degree as total? 50. And then minus the probability of intersection. How many with a college degree, with no college degree and male? No college degree and male, 15. Minus 15 out of 100. And this answer is going to be 34, 50 minus 15. 35 plus 39, I think it's 69 out of 100. And yes, it's the same answer, right? And for the third one, I think you can complete it, this one. Anyway, here you have the answer. Of course, these exercises are like the ones that you're going to see in your assignment on web work. All right. This is other example where we have a similar case where we have a probability table. It works more or less in the same way, but in this case we have exactly the probabilities. In the previous case we had we didn't have the probabilities. Of course, we can be able to compute them, but here we're going to have exactly the probabilities. But in the end, it's going to be more or less the same. Well, this says a firm has classified its customers in two ways, according to whether the account is overdue and whether the account is new, less than 12 months, or old. An analysis of the firm's records provided the input for the following table of joint probabilities. And there you have. You want to know the probability for the intersection of new and overdue, then it's going to be 0.07, probability of new and not overdue, 0.1, probability of old and overdue, 0.5, and probability of old not overdue, 0.33. So this is giving to you the probability of intersection of each concept. In each cell, you can see that. Then it says, one account is selected at random. If the account is overdue, what is the probability that is new? Well, in this case, for the part A, notice it says if the account is overdue, the condition or the restriction is this one. If the account is overdue. If the account is overdue. So restricted to that, what is the probability? So in this case, we look for probability of new given overdue. And in this case, it's the probability of new intersection with overdue divided by probability of overdue. And what is the probability for the intersection new and overdue? 0.07 divided by the probability of overdue. In this case, it's given directly. Overdue, you have to add these two probabilities, 0.07 and 0.5. So the total for this column is going to be 0.57, and for this one is going to be 0.43. So we need this probability of overdue is 0.57. And if you compute this, you will realize that the probability is 0.21228, well, this number here. Next question is, if the account is new, what is the probability that is overdue? I think you can compute this probability and verify this answer, right? What is the probability, next example, what is the probability that at least one of a pair of a first dice lands up 2, given that the sum of the dice is 7? All right, so in this case, we are going to need the sample space when we roll a pair of dice, 2 dice. You can do like this. It's going to be 1, 1, 1, 2, and so on, right? Up to 1, 6. What I'm putting here, each of these pairs is representing the possible outcomes in the 2 dice. For example, one possibility that in the first die, we can see 1, in the second one, 1. One other possibility is that we can see 1 in the first die and 2 in the second one, and so on. So we can continue in this way. You want to be very sure about your answer. You can compute the sample space first. No problem. But notice how in this case we can skip some computations, right? This sample space is going to have 6 times 6, 36 outcomes, and each outcome is supposed to be a pair. On the first element of the pair representing the first die, and on the second one, the second die. But the question is not about that. The question is more precise about what is the probability that at least one of a pair of a first dice lands up 2, given the sum of the dice is 7. So what about, notice, this is restricted because it says here given sum 7, given when the sum is 7. So I think we can, if we define event B or A, I'm sorry, if we define B, the sum is 7. B is the sum is 7. So we have to find only the elements in B, right? For which pairs we have only the sum equal to 7. Uh, Outcomes where the sum is 7 is going to be 1, 6, 6, 1, 4, 3, 3, 4, 5, 2, and 2, 5. And I think those are the possibilities when the sum is 7. So B is an event of the sample space. And now we want to compute the probability lambda 2 given the sum is 7. So now let's define the event A. We observe 2 in either die. So this probability is probability of A given B is equal to the probability of intersection divided by the probability of B. So here, no, I'm sorry. I think we can compute it directly in this case. I mean, we are not using this formula in this case because we're going to compute it only by counting the number of elements where we see 2, but only in this event. So in how many of these pairs we have the number 2? We have the 2 here and here. I mean, no matter whether the 2 is in the first position or the second one, the point is that we have the 2. It's here and here. You see? How many? 2 out of 2 out of how many elements we have in the whole event? 1, 2, 3, 4, 5, 6. So the answer should be 2 out of 6. Or we're the same, 1/3. You see? And it's the same probability we have here. All right. Now, related to the concept of conditional probability, the concept of independence. We know that the probability of A given B can be computed or defined as probability of intersection divided by the probability of B. But what if probability of A given B is the same as the probability of A? How can we interpret this? In this case, we say that the occurrence of B does not affect the occurrence of A. So that we can say that A is independent from B. So if we have the case that the probability of A given B is the same as the probability of A, remember this means probability restricted to a sample to the event B, but this is probability in the whole sample space. What happens if when we restrict the probability for A given to an event B, it's the same. If it doesn't change, we can say that no matter whether the event B occurs, then since the probability of A is the same, then A and B are going to be independent. Yeah. And what is the formal definition for this? Well, the idea is from the definition. Notice we have this probability of A given B. We know that this is probability of A intersection B divided by the probability of B. But if they are independent, then this probability is going to be equal to the probability of A. If independence. So in this case, we're going to have probability of A intersection B divided by the probability of B equal to the probability of A. Or in other words, the probability of intersection, it's simply the probability of A times the probability of B. And this is the definition. Definition of two independent events. Let's see one example. The idea of independence is that if we know that two events A and B are independent, the probability of intersection can be computed very simple, right? Only the probability of the product of A times the probability of B. Example, a fair coin is tossed twice. Find the probability of observing two heads in the two tosses. So we're going to describe this in the next way. A is going to be the event, head, and the first toss. B is going to be head in the second toss. So we look for probability of head in the first toss, head in the second toss. So it's going to be probability of A intersection B. But can we assume independence? Of course, we can use the definition to verify whether we have two independent events. But one of the main applications for independence is that many times, depending on the problem or the context of the problem, you assume independence. Why? Because in that way, it's simpler to compute the probability for the intersection of A and B. So in this case, but of course, it must be reasonable that we can assume independence, right? But I think, in my opinion, in this context, it makes sense. It makes sense that I observe independence. Intuitively, what is the meaning for that? In this case, it's going to be that when I toss, what I observe in the first toss is not going to affect what I observe in the second toss. I think that it's something that we can assume, right? And if we assume that, then we can say that the two events are independent. And if the two events are independent, then the probability for the intersection is only the probability of A times the probability of B. Again, I'm not saying that we cannot verify independence in other way. We have a definition to verify that. The definition is this one. But many times, for many examples, not all of them, do we have to assume that two events are independent? Why? Because in that way, it's going to, I mean, of course, first because it's reasonable to assume that, and in that way, you can compute the probability of intersection in a simpler way. So in this case, it's going to be what? Probability of intersection B is only, what is the probability that we observe head in the first toss is 1/2, assuming we have a fair coin, and in the second toss it's the same, it doesn't change, 1/2. So the probability that we observe two heads is 1/4, you see? And so on. What about if I toss the coin 3 times? Will be 1/2 times 1/2 times 1/2. Assuming what? Independence. Independence, right? Examples. Suppose that A and B are two, notice, independent events for which probability of A is 0.23 and probability of B is 0.8. First, find the probability of A given B. What is that? Well, notice, if we are said that the two events are independent, then the probability of A is 0.23. The probability of A given B, if they are independent, should be the same, right? So in this case, it's the same, 0.23. What is the probability of B given A? If A is independent from B, then B is independent from A. So in this case, should be the same. The probability for B, 0.8. What is the probability of A and B? In this case, probability of A intersection B, if the two events are independent, is probability of A times probability of B, which in this case is 0.23 times 0.8. Which is 0.184. Probability of A or B, this is the probability of the union. Remember, the probability of the union is the probability of A plus the probability of B minus the probability of intersection. Is going to be 0.23 plus 0.8 minus 0.184. Notice here, even when we don't have a real contest here, we are given only the probability of A and B, and with that we can compute all of these probabilities. Because why? Because we are assuming independence. You see, assuming that the two events are independent, we can compute all of these. For example, the probability of the union. The probability of the union is only this. which is 0.846. Again, these computations were made assuming or under the hypothesis that we have independent events. Finally, this example. For two events A and B, we know the probability of A and probability of B. This is similar to the previous example. If A and B are independent, then find the probability of the union. Probability of the union, the same as before, is equal to the probability of A plus the probability of B minus the probability of the intersection. But since we have independence, then this becomes only probability of A plus probability of B minus this probability becomes only probability of A times probability of B. So in this case we have 0.7 times 0.1 minus 0.7 times 0.1. Oh, I'm sorry. This is plus 0.7 plus 0.1. And this is 0.73. The same answer we have here, of course. 0.73. What is the probability of A given B? Since the two events are independent, probability of A given B should be the same as the probability of A, right? Which is 0.7. Probability of intersection is the product of the two probabilities, 0.7 times 0.1, which is only 0.07. And here, be careful. Here the hypothesis has changed. It says if they are dependent. So we cannot assume independence anymore, right? Probability of intersection. Well, in this case, we have to manipulate the things a little. For this part, remember that probability of A given B is equal to the probability of intersection divided by the probability of B. So we're looking for this, and we know this, and we know this. Then we can solve for that. Probability of intersection. I'm sorry, my B is very weird. It's only the probability of A given B times the probability of B. See that? In this case, it's 0.3 because of this times probability of B, that is 0.1, which is 0.03. And the same as this one, see? What is the probability of B given A? Finally, this question, B given A, notice. In this case, the formula for the probability of B given A is the probability of A intersection B divided by the probability of A. But we also know that the probability of the intersection, notice this one, we already have it, and it's equal to this. So what about if I plug this part in here? So we have, well, probability of A given B times the probability of B divided by the probability of A. And this is going to be 0.3 times probability of B, 0.1, divided by the probability of A, that is 0.7. So again, probability of B given A, by definition, is the probability of intersection divided by the probability of A. Probability of A intersection B, we cannot assume independence anymore, but no problem. We have probability of A intersection B before. So this is the probability of A given B times probability of B. So my formula becomes probability of B given A is the probability of A given B times the probability of B divided by the probability of A. We know all of these numbers. So substitute 0.3, 0.1, 0.7, and the answer should be this one you see here. Verify that. All right, see you in the next video.